Welcome back to the second half. I'm going to hand over to Barry Lock now. First of all, big thank you to Lotobacco, our main sponsor today, and have helped financially to put this event on. So thank you very much to Barry. Barry's and Lotobacco sponsored a few of our events, and so I'm going to hand over to Barry now, who's going to talk about intelligence first.
Right. Well, as I said, I'm Barry Lock. Work for a company called Lotobacco, and it's Mr. Lotobacco's money actually, so not mine. So he's very generous. I must admit I signed the check and everything, but that's by the by. What has come up from conversation with a couple of people outside before we came in here is I'm talking about debugging embedded software. The software that's running on your phone, the software that's running in your car, the software that's running in your set-top box, your TV set, and so on. I'm not talking about applications running on a Windows machine or anything else. Most embedded microprocessors have debug ports on them which allow you to connect into the processor to see what's running on the core and to then debug it, get it to work and analyze what's happening. And a lot of my conversation is about a second generation of debug port, which is called a trace port, which gives you information on how the program flow runs through the core so that you can actually analyze what the program flow did, where it went, what it wrote to, how long it took, timing, best in case, worst case, and so on. Now, for those who aren't into the embedded side of the market, I know 30% are from the people I've been talking to outside. The embedded side of the market is becoming very, very critical for your lives. Your car has now got, if it's a brand new one, new model coming out, they're putting collision avoidance systems in it. They're putting electric steering in it. They're putting electric brake control. So electric is your ABS and your monitoring of your braking system is all controlled, and your stability control is all controlled by a microprocessor somewhere that might or might not have been debugged properly. And some of my customers, it might not have been debugged properly, but that's a by the by. So if this is not applicable to you, I'm sorry for that, because I might have targeted the presentation at slightly the wrong people, but we'll see. The problem we've got, I'm talking about debug. Debug is not a sexy product. It's not something you go to bed at night dreaming about. Well, I do sometimes, but they're nightmares. It's the problems you didn't want, didn't plan for, didn't expect. And you end up in a dead end somewhere. But, and this is the critical bit, even though you don't think about it at the beginning of the project, 70% of the debug time on average, or sorry, of the software development time on an embedded project is spent debugging the problems that are in the code. If you don't realize how much, a modern Android phone probably has 300 million lines of software in it. Your engine management system in your car will have about 20 to 30 million lines of software in it. Nobody writes 30 million lines without putting mistakes in. So you have the new project meeting. You're all fired up. You're all going to do your new whizzy engine controller or whatever. So you define a system spec. You define the processor. You're doing all the great things you're going to invent on this project. Does anybody mention debug? In 70% of our customers, the answer is no. They don't even think about it at that point. Yet, to be honest, if you don't get that right, the rest of it isn't going to work. The volume users of silicon in the world, the Qualcomms, the Nokias, the Ericssons, this sort of people, they define how the system is going to be debugged when the silicon is being designed 2, 3, 4 years before the project. So when the new cores for your Samsung phone are being developed, the actual debug core was probably designed 2 to 3 years before. For those who aren't in the really big companies, you've just got to choose what you can get out of the catalogue. Sorry about that, but that's the real world. The main debug technologies. I've missed one off there actually. Probably the most used one in the UK is prayer. You may well laugh, but 3 or 4 years ago, I got so hacked off with this as a problem, I was actually evaluated buying louter-back prayer mats for the customers who wouldn't buy tools, and I was going to give them away. But I discovered the only way you can buy prayer mats, they come in bales of 200 plus from China, and they wanted an order for 50 bales at a time. I could have got rid of them all, but anyway, the main things people use, instrumented software. By that I include anything from printf to all of the proprietary programs out there. If you've got really old and slow cores, such as 68000s and Z80s, and any of you from the military will still be doing those, we make in-circuit emulators for them. But for the modern cores, there's a JTAG debug port. Almost every embedded processor, and we list 6,000 variants at the moment, and we know there's several thousand we haven't listed because we just don't have enough people to do the list. And a lot of the modern ones have now got a program flow trace port on them as well. Let's have a quick look at those. JTAG debugger. It reads a JTAG chain within the core, which is a serial chain which goes around various peripherals within the core. You can set breakpoints, you can read the memory right to the memory, you can read the registers right to the registers. Some systems will provide some profiling and similar sorts of things, but this depends upon what the silicon vendor decided in the goodness of their heart to give you. But you get no historical information. You stop the core and you look, and you can see where things are and what's been written. But you've got no historical info on how it got there. It got there by magic. Program flow trace systems collects data on the program flow whilst the core is running. This is real-time, non-instrumented. This is what the core did. This is where it went. So you know everything it's done. If you know everything it's done at the point where you stop, you can scroll backwards and forwards through it. So you can go back to find out where that variable was overwritten, where the wrong value was written in. You can scroll back and search for all instances of a particular write or something like that. It also gives you code coverage without instrumentation. If you're trying to do safety critical, or anything that requires certifying to a specification, medical or automotive or whatever, code coverage is one of the things that's normally mandated. It also gives you best and worst case timings, analysis of cache, and so on. The next few slides that we go through, there's a lot of detail there. You can go through them all at your leisure. I'll skip through them fairly quickly because going through them in detail like this doesn't help a lot. It doesn't show on that screen, I don't think. The bottom half of that is pink and the top is a very light green. It's meant to show running from core 1 to core 0. The second column across, you've got number 1 and then number 0. It's a 2-core system and the code switching from core to core. The 2-core system running in SMP mode where the code switches dynamically from one core to the other. That's an example of the actual program flow. The same done as a graph for each core. So that gives you some information to help with debug. You've seen where the code has gone, you've seen what steps it took, you saw where it went, you saw what it wrote. Now, we can take it to things like code coverage. There's graphs. You go the first part of the code in that picture was never actually run, then some partially run sections of code, and then 100% run. With statistics on size of code and so on. You can sit down at your leisure and go through those. As I said, the slides are all in the brochure. For those who have managers, there it is in graph form. The yellow code was never actually run. The white line was. So you can show it to your manager and say, that's what it did, boss, because you can't expect managers to read numbers. A more detailed view down at line level. Then we can start to do performance analysis. Because you've got your program flow, you've got the call nesting. So you can see it actually nesting from function to function, time in each function, time in any daughter functions, times for interrupt handlers, and so on. Another detailed view of function nesting, interrupts, and so on. All of this data, all of these graphs can be exported in a format that you can put together to use for your code approvals. So if you have to go for an approval at the end of your project, all of this can be exported and packaged up to go as part of the approval process to prove that the code did run, and it did run in a timely fashion, and did worst case time was acceptable. Step back up to high-level language and timings. Oh, an interesting thing, by the way, one of the variants of our tools will actually give you power as another column, so you can do microjoules per function as the code is running. Which, if you're running a mobile phone, is superb, but you'd be surprised, one of the things that was most critical on power that we had recently was a project for a tank. They had so much electronics in this tank, there was actually more electronics than there was electric power available within the tank. We did try to get an actual test drive in the tank just to see how it went, and they said, you'll have to fund your own airfare, it's in Afghanistan. Call trees, again, analysis. Once you've got data from a program flow into a file on a computer, the ways in which you can analyze it is only limited by your imagination. So we can analyze it almost any way we want. We can even generate pie charts for those with proper management. Another graph. Anyway, I've been saying about trace ports. If you're going to do an embedded project, choose a core with a trace port. We list something like 25 different families of cores that have trace ports. They're the most popular ones. In fact, the most popular by a long, long way is ARM cores. Currently Cortex-A and Cortex-M, Cortex-M microcontrollers and Cortex-A for high-performance systems. The PowerPCs, they're used automotive. If you've got a modern car outside, you'll probably have half a dozen of those in it. Engine management, gearbox management, braking, stability control, and so on. I said earlier on about the number of failures in systems, in designs. Out of the new designs we see in any 1 year, within 2 years, something like 70% of the projects have closed without ever getting out the door. This really winds me up, because a large percentage of those projects, as the projects fail, so do the companies involved. Which means every year I have to go and find 30 new customers just to keep my customer base up to scratch. If you look at my customer base now compared with 10 years ago, there are only 3 companies on there that were there 10 years ago. Qualcomm and Samsung are the 2 main ones you know. All the others gone by the by. All their UK offices have changed, been bought out, and so on. The biggest failure we saw, by the way, was 120 people got made redundant because a manager wouldn't spend £16,000 on a respin of a board to get some debug data. He went as well, by the way. What worries me is he'll turn up somewhere else. Anyway, talking about failures on designs, ARM are really, really concerned because they get royalties of 10 cents per piece of silicon going out the doors of their end customers. They don't get paid for the designing the IP. They get paid by selling the designs to Texas Instruments, for example, who sell the chips to Nokia or Samsung or whatever. They only get the royalties as the things go out the door. So there were so many ARM designs failing, they took some fairly detailed measures to try and get the success rate up. Same with Freescale and Infineon. Let's actually show you what they did. This is the Freescale solution. It's on the new PowerPC cores for automotive. You take, for your development systems, to get the data out of the development system so that you can see what the core is doing, you take your production chip, and on the production chip, there are some bond pads in the center section which allow you access to all the data buses and the memories and so on. Now, some of you here are from a couple of local chip companies. You might not have seen this one. It's not confidential, by the way. It is on their website. What they do is they put a buddy device on the top, which extracts all the data they need for debug, so that your actual production chip, which is the bottom one, is the chip that's going to go in production, running the silicon, running the code and software that's going to go in production. They actually build one device on the other with little copper pillars and solder in between. Now, if you think of the scale of chips, that's not an easy thing to do. As a silicon man myself from a long time ago, I am totally in awe. When you actually come to do this, you've got your basic footprint, which is 176 pin, but the debug version of the chip has, I've lost the numbers now, maps up to 324 pin, which enables you to get out your trace data, your all the details of what's happening on the buses internally. And all you do is you remove the interlayer packages and you're into your production unit. ARM put some very complex debug silicon into their chips. That's what's in the current Cortex-A's and Cortex-M's. Debug Silicon is now a very high percentage of the chip area. In fact, on the first versions they did on the Cortex-A's, the Debug Silicon was 50% more than the actual core silicon area. They then had to remove some features from that so that they got back down to a sensible level. But that is in all of your Cortex cores. Again, if you want to look it up, it's Core Site on the ARM website, and all the details are there. For those who are doing designs using silicon, first, read the manual. And I'll say it again, read that blank manual. And read the errata. Some of these modern chips, the errata can be a 1,000-page PDF. The main manual's 5,000 pages. But every time we go back to our head office and say something's not working on the tools, the normal answer is, it's a bug in the chip. Hasn't the customer read the manual? Which leaves egg all over everybody's faces. Before you start, work out how you're going to debug it. You will get the bug from hell. You know you will. There's a guy called Murphy who wrote all these laws that said you'd get it. We've currently got a customer with a telecoms design. It's now 3 years late to market. I wonder how long that design center is going to stay open, because it's part of a multinational company. And the owners of the group will probably close the local design center. We had a design for a car dashboard 3 or 4 years ago. It was 7 months late to market. You imagine telling Ford that they're not going to get their next car out on time when they've done all the press launch and there's a factory building cars and there's no dashboard. Those engineers were not happy. Then, not only have you thought about how you're going to debug it, are you actually being stupid with what you're thinking about? We've seen a Linux-controlled street light, and it only had to come on and off at dark and light. We've seen a Linux-based gas meter. It wasn't actually communicating back to head office. I could have understood that possibly. This was only giving you a display in the kitchen of how much you were using at the time. They could have been done with an 8-bit PIC, but they weren't. They were done with a 32-bit processor with Linux on it, because Linux is free. Both companies were VC funded. Both companies had their BMWs on lease for a year or so, and then everybody got fired. It's sad, is all I can say. I started off saying think. Please think about your project before you start. You're all mature people. Things will go wrong. Think about how you're going to debug it, how you're going to get it working. Please. I'm not saying buy our tools. Just look at the market, buy somebody's tools, for Christ's sake. We have several competitors. Evaluate ours and theirs, because you'll always buy ours in the end, but that's by the by. That's it from me.
Thank you, David.